So this is slide 11 from where I have to start. Previously, we saw something about recursively defined sequence, and I told you yesterday that some sequence will be given to you, and maybe the recursive formula for that sequence along with the initial condition like that will be given to you, and then you have to compute the values at different positions in that sequence. You can also, this is something related to exam, but you can also design these recursive formulas, and these formulas that you are seeing are designed by the people, not by some other creature of this universe. Anyhow, so now we have the recursively defined functions. So you can define these functions with these two steps. I am going with a little bit pace because these are some theoretical stuff. So you can define some function with two steps for the set of non-negative integers, okay? And the first step is again the basis step, and the second step is not inductive step. It is not mathematical induction. It is recursive step. And in the basis step, you will see the value of the function at 0. You will give 0 to that function, and you will see how that function will give you the final result at 0. And then the recursive step is that you will define some rule, and this rule you will define for finding its value at any integer. It means that you will give any number to that function, and that function will have some recursive rule or recursive form or recursive equation. So, and then you will give some number into it, and that function will give you some value by using the smaller values of that function. Because the name is recursive step, so in this step you will have some recursive formula for that function. And then by using that recursive formula of that function, you can give any integer to that function, and that function will give you the value. For example, now here you have that example that suppose that function f is defined recursively by two steps. And what are those steps? This is the basis step. F of 0 is equal to 3, which is given to you. And the recursive step, f of n plus 1 is equal to 2f of n plus 3. It is also given to you. Now the question is find f1, f2, f3, and f4. So these are quite easy things. It's not something difficult. So this is the basis step, and this is the recursive formula which you have for this recursive step. And by using this formula, you can get the values for any integer. And here the question is find the values for 1, 2, 3, and 4, where f is a function. So now it's easy. So f1 would be, so f1, which means this is now f0, okay? If you are finding f1, which means you are putting n as 0, okay? Then 0 plus 1, it will become f1. So f1 would be 2 into f of 0, yes. 2 into f of 0 plus 3, and f of 0, you have the value for the f of 0, 3. So 2 multiplied by that 3 plus this 3, and you have the 9. And similarly for f2, you can have, this would become 2f of 1 because this is the previous value, small value, and this is the next value you are getting. And in this way, you can find all these values. It's easy. It's not. So that's why I have not given too much examples of here. It's quite easy, even in the book. Now, the third definition, recursively defined sets. Because this section 5.3 is about definitions. So you cannot expect too much complicated thing in this section. All things are just like definitions. All things are like definitions for this recursive behavior. So then we have the recursively defined sets. So now you can understand that set, if A is a set, then in the curly brackets you have the elements. So maybe it would be very much close to the function. But function normally takes some value and normally it finally gives you the value after mapping. Like you have here, it is taking some value and then it is giving you from some value. After mapping, mapping is what? After calculation here on the right hand side. Anyhow, the basis step. Now for sets, again you have the two steps. The first step is basis step, second is recursive. So it is very much similar to the previous approach. But here in the basis step, it is written here that initial collection of elements is specified. By the way, it depends on the sets, what type of set will be given to you. And you know that, for example, set of strings or set of characters. I don't know, you didn't have studied theory of automata, so, but you have the knowledge of mathematics. Null string or empty string or empty or null is always the member of any set. This is according to the definition. If you have a set with numbers, then you can say null is always the part of that thing. Or if that set is with the alphabets or the characters and then making strings by using those alphabets, then null's empty string is always the part of that whole set. Anyhow, here basis step is that initial collection of elements is specified. So for the set, initial elements will be specified. Specified means will be described in the basis step. Will be described. You have to write the initial elements in this basis step. And you will see this step, this understanding will be clear when we will see the example. And recursive step is again the same. You have to build some recursive formula like thing, but that can be like function, but function is something different because here you have the elements in the form of a list, in the form of a set. So you will have some recursive formula, and that by using that recursive formula, you will generate new elements for that set. New elements for that set. That is written here. So you will have some rules, and that rules would be recursive formula. And we will use these formula for forming new elements in the set. Okay. And we will use the existing elements and we will form the new elements for this set. For example, here we have the set is, this is not sigma, okay? This is not sigma that you have in mathematics. Here sigma means input. It means the subset. You can call it a set, sigma. Sigma is a set now. Here it is, sigma is not for summing up things, okay? Here sigma is a symbol. to represent a set. So if sigma is 0, 1, so now this is a set which is containing elements 0 and 1. And these 0 and 1, normally in the subject of theory of automata, we use this symbol sigma, okay? And we used this symbol sigma star if we have strings generating from this set, then we can represent those strings in the form of a set like that, sigma star. So sigma star is representing the strings which are generated by this set, which are generated by using zeros and ones. Okay, this is theory of automata, but I am not, I cannot explain all those things, but I will give you a little bit introduction. Because this is something in theory of automata, this is the beginning point where you learn something that how you can start with this set with input symbols, and those input symbols then you can use to generate a language for some machine. Automata means machine, okay? So if sigma is 0, 1, so now this is a set with input symbols 0 and 1. So you have 0 and 1 in this set. For example, for Arabic, you have character sets starting from alif to ya, and you have different. By using those characters, you are producing different words in Arabic. So you, if you are a machine, then that is your character set. That is your set from alif to ya, and you are using those characters to produce different. If you are talking Arabic with me, I don't know, anyhow, if you are talking in Arabic with me, then you are saying some words. So those words is a collection of those characters. So you are using that, basically unconsciously you are using that character set. So now that character set is sigma, which have these character set, and that sigma star is your mind. You have those words in your memory, okay, and which you are throwing, and these are basically those words. So now you will understand. If sigma is 0, 1 are the input symbols of a set. So this is a set and these are the input symbols. And then sigma star would be lambda. Lambda is an empty string, okay? 0, zero separately can also be a word. 1 separately can also be a word. 0 with 0, 0 with 0, 0 with 1, 1 with 0, 1 with 1. So you can see all these things. You are mixing characters, you are joining characters. And then 2 times 0 with again 0, you have triple. 2 times 0 with this one, you have this. Now I have considered this one. So these are the strings. I can call them W's. I can call them word. So I'm using W for word. So these are the words. And these are, for example, characters. But here in this example, I can call them X. Okay. So here, there is something written here which is recursive. Okay. So the recursive definition here is W belongs to sigma star. So you know that these are string words. So this is if W belongs to sigma star and X belongs to sigma. X is the character. X belongs to sigma. Then you can combine this W with any X, and then you will have the new word that would belong to this sigma star. Okay. For example, if this is my W, I can combine this 0, 0 with this X 0, and I have my new word 000 here. And this way you can go on. So this last thing is a recursive formula for this set. And now basis step is what? The empty string, the starting, the initial collection of elements. So whatever the starting element available in the set, that would be your base. So lambda lambda empty string, which is specified in sigma star, is the basis step. And then recursive is after lambda. Okay, you in the first step you can generate 0 from here, and then you can generate 1 from here, and then you can take this w, combine it with 0, then you will have 0 0, and then take this 0, combine it with 1, and you will have 0 1 by using that recursive step. So this is the example for the sets. And similarly, you have these further definitions. I have mentioned it here, read it by yourself, but I will start a little bit so that it will not be an issue for you, because you don't have the idea of theory of automata. So that's why I will just only give you an idea. Here, this definition 2 is saying something about concatenation. Concatenation means when you join two strings. When you join two strings. And here sigma is the same as you have in the previous example. Sigma would be the set with input symbols, and sigma star would be the set of strings. Okay. And these strings would be formed from the symbols of the sigma. As you know that these strings sigma star are formed by using these symbols of sigma. Now we can define the concatenation. Now you have to define something for the concatenation of strings. Concatenation of strings. When one string will concatenate with other string. So again, here you have the basis step and the recursive step. In the basis step, you know that now you have to concatenate. So lambda is the first element in the set, empty string. But you have to concatenate. So that's why if we will take some word from the sigma star, then you have to concatenate that word with the lambda, and then you will have the word, because lambda is empty. Because lambda is empty. This is the basis step. So you have to concatenate. You can concatenate each word from sigma star with lambda, and then you will have that word. Recursive step. So this is definition, okay, for concatenation. For concatenation. And now, and concatenation of strings. And how strings are formed? Strings are formed from the input symbols, or the character set. The set in which the characters are available. In this previous example, what is the character set? Sigma is the character set. Sigma star is the string, or you can say set with strings. You can say sigma star is a set with strings. Infinite set with strings. And this sigma is a finite set with input symbols or characters. So now for concatenation, if word 1 belongs to sigma star, yes, okay. And if W2, word 2 belongs to sigma star, if you have taken two words from the sigma star, and if X belongs to sigma, then X is available in the input character set, then what you have to do, you can do like that. Word 1, and then you will combine word 2 and X first, and then you will apply the multiplication dot product between with the first, which is the concatenate. Or you can join or concatenate the two word 1 and word 2 together, and then you can join X with that one. It is just joining. If these are the strings, then this is nothing except joining. All the things will be joined together. For example, here, give a recursive definition for length of word. Length of this W means word or string. So the basis step would be, for this, we are considering string, we are considering characters. So always the basis step would be lambda. And lambda, what is the length of empty string? Zero. So empty string has zero character actually, but it is the part of the set. So that's why it has the length 0. And here length of wx. W is a string, x is a character from the input symbol. And so you can write it as length of w and length of x is 1 always because it is a character. 0 has length 1. This 0. What is the length of this one character? 1. What is the length of this one character? 1. So that's why this 1 is mentioned here. And this word can be a collection of characters. So here, whatever the length you have, you can write it here and then plus 1. That would be the length of this W. If W belongs, and you know that W belongs to sigma star and X belongs to sigma. So read it by yourself now. This definition is, sorry? What is digital number? What you are asking? Okay, yeah. Yes, definitely length is 3. If you have these, what is the length? This is according to the programming language, nothing else. So these 3 characters are there, so length is 3. Length is 3. It can be 4 if you have 2, if you have 4 characters in it. And here definition for rooted tree. What is rooted tree? A tree which have the root. Simply. Where a rooted tree consists of set of vertices. If you have the tree, in the tree you will have the nodes, the vertices. You have seen the trees in other courses. Is it true? Then if you know the tree, then you know that in the tree you have the nodes. The other name is vertices. One node means one vertex. Nodes, plural. So vertices is the plural. So when a rooted tree consists of set of vertices, so rooted tree can consist of vertices and containing a distinguished vertex called the root. And if so, a rooted tree can have different nodes, but also a different node at the top, which is called the root, which is called the starting node. The starting node, which is called the root. You know the definition of the root node. And from that root node, you have further edges, and the other vertices are being connected with the whole tree by those edges. For this basis step, the first basis step is starting point is root. Starting point is root. We are not talking about, now the definition is different. Okay, we are not talking about basically the sets, we are talking about trees. So the basis step would be a tree with one node. That would be the root. So that is the starting point. Recursive step, for example, suppose if you have T1, T2, and Tn, these are the different rooted trees. Exact word is disjoint, but I am just giving you the other word different for your understanding, nothing else. So if T1, T2, and Tn are different rooted trees, so these are the different trees, T1, T2, and Tn. Then they must have their roots. If they have their roots, then we are saying that they have the R1, R2, and Rn are their roots respectively. If this is the situation, and if now we want to make a graph, starting with the root R. So now we have another node R. Now we have another node, single node, which we are calling R, which is not in any of the rooted trees. So this node, this single root R is not in any of these trees, is not the part of any of these trees. It is separate. It is separate. And now we want to add an edge from all these trees, T1 to Tn, to that root. Simply, I don't, for example, if it's easy, it's not. When you don't give expression on your face, then I normally take an idea that you are not understanding. It's not difficult. It is saying that T1, T2, and so on here. If these are the trees, and we have this root. We want to add this root to this one. So simply you have to do that. Nothing else. If we, so, which is not any of the rooted tree T1 to Tn, and adding an edge from R to each of these vertices. So this, what are the roots of this tree? What is the root? R1. What is the root of this tree? R2. What is the root of this? Rn. So now it's okay. So adding an edge from R, from this R, to each of the vertices R1, R2, and Rn, what you will get is again rooted tree. So this is not, this is just easy things. So that's why I have mentioned here, read it by yourself. But your faces always remains blank and silent. Structural induction. Walaikum assalam. So this is another thing, structural induction. So mainly we focused on mathematical induction. Then we saw a little definition of strong induction. And now we have again the definition or the understanding about structural induction. So structural induction is very much similar to mathematical induction. The only difference is that mathematical induction has the domain what? Positive integers. What is the domain of mathematical induction? Positive integers. And the domain of structural induction is recursively defined structures. It is not talking about numbers. It is talking about something recursive. That is the domain of structural induction. That is the domain of structural induction. Recursively defined structures. And what are the recursively defined structures that you have seen? Sets, functions, sequences, all are, for example, they can be defined recursively. So now, leave this point. This is saying that sometimes structural induction is not, sometimes structural induction does not perform good in comparison to mathematical induction. This point is saying. So mathematical induction is always have the more importance as compared to these structural induction, or even you can say the strong induction also, but it is more true for this structural induction. Now we are going to, this is basically a question, but I have given him the heading claim 1, because structural induction you used to prove some claims, hypothesis. So that's why I just changed the heading to claim 1. Otherwise, it is not a claim. And this is also available not in the book. Okay. So what is this saying? It is saying that we have a non-empty binary tree. What is binary tree? Which have 2 children on each node. That is binary tree. So a non-empty binary tree T is either have a root node R with no edges. So that is the base. He's saying that the non-empty tree, we have the non-empty tree T either with only one root node without further edges, or a root node R is pointing to two non-empty binary trees, or you have the binary tree, or you have the, so there is, we have the non-empty binary tree T, and that tree has two situations. Either what is the base situation? It has only the root node. This is what you have seen here in definition 3. And the other situation is that it will have the sub-binary trees. Either this is the situation only, or it will have further. It will have further left and right subtrees, or a root node R pointing to two non-empty binary trees TL and TR. So now this is TL and now this is TR. So this is the recursive step, or you can call it inductive step. So the claim is, with the claim that the size of the vertices, size of the nodes, total number of nodes in that tree is equal to total number of edges plus 1. This is the claim. If you have the binary tree, the size of the nodes, total number of nodes, you can calculate by finding the total number of edges and add 1 into it, and then you will have that total number of nodes. So this is what written here. What is this one? Number of edges. What is this one? Number of this is number of vertices, this is number of edges, and then plus 1. So this is the claim. We have the non-empty binary tree with single root or with the TL and TR, and the size of vertices is equal to size of edges plus 1. Prove it. So now this is a proof by structural induction. Okay, and structural induction is again like, we don't, here we have the base case, inductive hypothesis, inductive step. So it is again very much similar to mathematical induction. Let's see what will happen. But we don't have PK and PK plus 1 here. Okay, we don't have PK and PK plus 1 here. That is something. Okay. Proof. So now we are just starting. We are just writing. The T is our non-empty binary tree, and P has the proposition that we want to hold. What is that proposition? This one, the claim. And also this information, either single root or the TL and TR, but this is the major claim, which we want to hold. Hold means which we want to see it as a true. What is the inductive step? Inductive step, base case is when you have only single root. So if the binary tree T consists of a single root R, single root node R, then what? This is the claim. We have only one node. So size of vertices would be 1. And edges is what? 0. Right hand side will give you, put this in this, put here, and you will have 1 here left hand side, 1 here on the right hand side. So this is true. And we have edges 0. And we can say that this proposition P for root node holds. It is true because the left hand side is 1 and the right hand side is also 1. How? By using this thing. Number of nodes for single root node is 1. Edges 0 plus 1, it is also 1. So that's why I am saying it. Inductive hypothesis. So now this is something recursive, okay? This is something recursive. So in the recursive part of the definition, for a non-empty tree. Now, T may consist of a root node R. What is the recursive part? Root node R pointing to two binary trees, TL and TR. This is the recursive part. So in the recursive, we can say now the binary tree has the further subtrees TL and TR. TR is the right binary tree, TL is the left binary tree. TL is the left binary tree, TR is the right binary tree. So now we want to see that claim size of V is equal to size of edges plus 1 is also true for that definition, TL and TR. We want to show that PT is holds for that thing. But to prove that, suppose that VL is the vertices for the left binary tree, EL is the number of edges for the left binary tree, VR is the number of nodes for the right binary tree, and similarly, ER is the number of edges for the right binary tree. Now I can write that claim. Size of vertices would be number of vertices in the left binary tree plus number of vertices in the right binary tree plus 1. Why I am writing? Because if this is the tree, this is the number of vertices left, this is the number of vertices right, plus this one, which is a root. Okay. So this is the root node basically. This is the number of nodes for the left binary tree, this is the number of nodes for the right binary tree, and this is the root of the binary tree, which is you are adding. So this is the definition for the number of, for non-empty binary tree, for to calculate the number of vertices. And now I know that from that previous claim, vertices is equal to E size of E plus 1. So write it that way. So this is for size of left binary tree plus 1 is something for the left. And this is equal to size of right binary tree plus 1, and that is that one. So this is what? This was the inductive hypothesis. It has the two TL and TR, two binary trees, nothing else. So I am just putting that thing according to that inductive hypothesis, nothing else. Now simplify it. So size of EL, size of ER, and then this one and that one, you will have two. These are basically the total number of edges. This is the total number of edges for the tree, which you can write it as E, and then plus 1 is just remaining, which now you have. You have started with vertices and you have that left hand side. So now you can say that PT holds, that proposition for the binary tree holds. This is the example for structural induction. Basically, you can write it here, example 1. Okay. But I just renamed that example 1 with the claim because you can also use structural induction to prove something. So that's why I have just renamed that example with the claim 1. Now this is the actual topic. This is actual section 5.4, which is about recursive methods according to your CO. This is recursion methods, and the close words for methods is algorithm. So now, what is By the way, what is a recursive algorithm? The definition. I can give you a simple definition. A recursive algorithm is that algorithm which can call itself, which has that property of calling itself. That is called recursive algorithm. But here maybe you will have the definition according to the author of that book by Rosen H. So algorithm is recursive when it solves a problem by reducing it into a piece. Instance means piece. That piece is not me, has a meaning of aman. That piece is something small. I don't know. I don't know. What is the Arabic word for peace? Qatar? Qatra? Qatar? Kita. Okay. Now I'm okay. Qatar. Okay, Qatar. So the algorithm which will reduce the problem into smaller problems, and then evaluate the result for those smaller problems, and then use that result for further upward smaller problems. So that would be some kind of a recursive algorithm. The simple definition is a recursive algorithm is an algorithm which can call itself, which can call itself. For example, if you have a program, if your program has a tendency to call itself, or if you have a function, or if you have a method in your Java class, if that method has a property to call itself, then that method would be recursive method. So anyhow, now, so if an algorithm, if it solves a problem by reducing it to an instance. Instance mean kata in Arabic, okay? Or kita, whatever you want to say. And then you will have not only one kita, you will have many kitas, because that many kitas will be according to the call. If the method is calling itself 5 times, then it means you have 5 katas. Okay? I am using Arabic and English together. Katas. So you have 5 pieces. Anyhow, now the example 1. Now in this section, we have to build recursive algorithms for different problems. This is what this section is. You have to design recursive algorithms for different problems. And this is now example 1. And the question is, give a recursive algorithm for computing n factorial. We want to calculate n factorial. So write a recursive algorithm for this n factorial. This can be a question in your course. And what is this n? N is a positive integer. So you have to design some kind of a algorithm is something for computer science people. Algorithm is something which is very much close to your programs because it is a serial code. So anyhow, the recursive definition. What is the recursive definition for n factorial? This is the definition. What is this saying? You have that n, if your n is 5, then that 5 will be multiplied with 5 minus 1, 4. So that now you will call it again. Now you have the 4. You are calling 4 here. Then that 5, 4, whatever, that will be multiplied by with 3. Leave it. Leave it and directly see this algorithm and you will understand. And this procedure This is the word only. It means method, it means function. And in procedural languages, you can write functions or methods with this keyword procedures. Procedures, okay? And the name of that, for example, in Java, you can write some name for the methods. But here, this is a reserved word just for algorithms, nothing else. If you are going to write some name for your and it is not necessary that you have to write that thing only because it is algorithm. Algorithms can be a little bit different, little bit similar or like that. There is no restriction. There is no restriction. So you can start with this, just with this name, factorial, and that method will take some number n, and that would be positive according to the example 1. If that number is 5, then we are checking here first if that 5 is equal to 0. Here we are checking a condition, okay? Here it is not, this is not programming language, okay? So this is algorithm. Here now we are not assigning this value to this one. No, don't take it as a programming language. Here this equal means and this if means that we are checking a condition, okay? We are checking a condition and not assigning any value. So if n is equal to 0, if the condition is true, then what? Return 1. You will come out of this algorithm. You will come out of this whole algorithm and the value will be returned as 1. 1 will be returned as a answer, as a result of this algorithm. So I have the 5. So my 5 equal to 0. This is condition. No, 5 is not equal to 0. So then the condition is not true. So I will go to the next part, this part. And here I have else. And after else, I don't have any if condition again. So this will be executed now on compulsory basis. So now else, what it is written here, return, come out. Returns mean come out of this algorithm. N multiplied with factorial into n minus 1. This is according to that definition, okay? Okay, nothing else. N multiply, and then we are calling this method again. We are calling this method again with this input value. And what is that input value? If you have n is 5, then 5 minus 1, now you have the 4. Now you are giving, first you are giving 5 here, but now you will have, you are calling this method again with value 5, with value 4, sorry. Your 5 is still at that position. So I am just writing it here. Your 5 is still there with this dot. And you are calling that factorial method again with value 4. Okay, call it again. Now your n is 4. 4 equal to 0? No. Then I will come here in the else portion. Now my n is whatever. So now what? 4. Now this will be 4. 4 dot and 4 minus 1, it will become what? 3. So I can write that previous 4 here and I can call this factorial again with 3. So 3 equal to 0? No, I will come here. And now this n is now 3. I am writing this 3 here. And calling this factorial with 3 minus 1, 2. With 2 again. With 2 again. When you will call 2 equal to 0? No. So I am writing that 2 here. And then 2 minus 1 with 1 again. Calling it again. N is 1. 1 equal to 0? No. Else writing this because now my n is 1. And calling 1 minus 1 with 0. Again. So now n 0 is equal to 0. Yes, return 1. So now that 1 will be returned here. Here, okay, as a result. So that 1 multiplied with 1. That 1 will be multiplied with 2. You have 2. 2 multiplied by 3. 6 multiplied by 4, 24. 24 multiplied by 5. Finally, you will have what? 120. 120. Here, just for your understanding, it is just mentioned here, just for your how this algorithm will, and output is n factorial. N factorial means this complete thing. Here, I'm just explaining that how this algorithm is working. The first call of this algorithm would be 4 factorial. When you will call this with 4, this statement will become 4, and then it will call 3 factorial again by using this n minus 1. N minus 1 will give you 3 factorial. So I am given this yellow color. So you will call it again with 3 factorial. And then you will again, it will go again with 3, and it will come what? 3 factorial will be like 3 dot and 3 minus 1, 2 factorial. And I have given it the blue color. So now you will call this factorial method with 2 factorial. This is the same understanding as I explained here, but with a different format. With respect to this call only, Then it will call this with 2 factorial, and how it will call? It will become 2 dot and 1 minus 2 dot 1 factorial. It is just showing that statement only, okay? These different colors. And then it will call 1 factorial, and how it will become? 1 dot 1 minus 1, 0. It is not. Now the problem is divided into small problems. 5 is further reduced to 4, 4 is further reduced to 3, 3 is further reduced to 2, and so on. And this is what? This return 1, n is equal to 0, then this is the base case. When your problem will reach here, the result will be returned, and it will be given to the all other calls that you have. So here, now 0 factorial. What is the 0 factorial? 0 factorial is always 1. Is always 1. So when it is 0, return 1 will be given. So that 1 will be given to here at this position, in this violet color. That 1 will come here, and then you will have that 1 factorial. What is the answer for that 1 factorial? What you will put here, and then you will have the answer 2. And now you have the value for 2 factorial. You have to put that value here up to this 2 factorial. And that will become 3 factorial. 3 and the 2 factorial has the value what? 2. So 3 multiplied 2, you have the 6. And similarly, now you have the value for the 3 factorial. You have to put that value here. 4.3 factorial, which you are seeing it here. What is the value for the 3 factorial? 6. Put the value here. You will have 24. This is the example for 4, not for 5, okay? And we have taken here example for 5. So this is the recursive formula for the, recursive algorithm for n factorial. Similarly, devise the recursive algorithm for computing b raised power n mod m. This is a question from maybe chapter 4, congruences. Have you seen that chapter? So this is some number, and mod m. So this is the divisor. This is the divisor for that number. Anyhow, this b, n, and m are integers. M can be greater than or equal to 2. So this m can be greater than or equal to n can be greater than or equal to 0, which means n can be some positive number. Power can be 0 or greater than 0. And this b would be greater than or equal to 1 and less than or equal to m. This b. This cannot be 0, okay? It should be greater than or equal to 1. So it can be 1, it can be 2 or whatever, but it should be less than 1. Anyhow, devise a recursive algorithm for compute. So if you have the numbers here and you have to compute, you have to calculate the, for example, if I will give 2 raised power 3 mod, for example, 2, how you will calculate it? So now the question is asking a recursive algorithm for this formula. Simple recursive definition to calculate this thing is that mentioned here. Simple definition. This is according to chapter 4. B raised power n mod m is what? B into just previous b n minus 1 mod m, b n minus, it should be in the same line, then you will understand. Anyhow, b raised power n minus 1 mod m multiplying with this b, and that whole is then again mod m. This is written according to chapter 4. This is equal to that one. This is equal to that one. Further, when you will divide it, that number sometime, when you will divide it with this m, that number can be even, can be odd. Okay, that number can be even, can be odd. So after division, if it is odd, then you will have the remainder, and if it is even, then you will have the remainder 0. So now we are modifying, now we have these definitions. All are recursive definitions. By the way, this is not needed here, but I have just mentioned for just for your information that this is also a definition according to chapter 4. But for your question, these are the definitions that you needed. This number can be even, can be odd. So when you will divide that with m, if it is odd number, then you will have the remainder, some value for the remainder. And if it is even, and if your divisor is, suppose if it is even, then you will have remainder 0. So now, if n is even, now we are supposing that if this power is even, b raised, for this b raised power n mod m, then we can write it as bn by 2, making it half, making this n half mod m, and then writing it with square. Half square is again the same thing. So this is equal to b raised power n. So this is equal to b raised power n. We are making it half bn by 2 and then square. First we are making it half, then dividing it. Whatever I will get, I will making it square and then doing mod m again. So this is just the understanding of that equation. How it is formed, it is up to that person who formed this equation. But the understanding you got. B raised power n, if the n is odd, if this n, if the power of this n, if this n is odd, then again n by 2, making it half, and then taking the floor function. Because if it is even, then half, you will get very much straight half. You will not get any points, something like that. But if you have the odd, then you can get that points. So how you can remove that point? By taking their floor function. It will ignore those fractional points. If you have 2.5, it will give you 2. If you have 2.7, it will give you 2. If you have 2.2, it will give you 2. Okay. So it will remove that fractional part. So b raised power n by 2 and the floor function mod m, the same thing again, square and then mod m of that thing, and that is that extra thing for that odd. So here you have done for the even thing. So even thing is clear, but that is something the extra for the odd number, which you are multiplying with that result, and you will have some result that would be finally further divided with this n. So anyhow, this is the recursive definition for the number for this formula when n is odd. This is the recursive formula when n is even. Now you can use these things in the formula, and then we will take some number, and then you will see how it is evaluating, and then you will get the complete understanding. So this is the recursive formula for now for this computation of b raised power n mod m, and the name of the procedure is m power, and we will give b, n, and m as integers. We have b, n, and m as integers, and we are giving condition b is greater than 0, m is greater than or equal to 0, and n is greater than or equal to 0. Now, if our input is like that, b is equal to 2, n is equal to 5, and m is equal to 3. If these are the inputs, b is equal to 2, n is equal to 5, and m is equal to 3. 2 raised power 5 mod 3. What we have? 2 raised power 5 mod 3. So if I can write it here, 2, 5, and 3. Now here n is equal to 0. This is my n, which is 5. N is equal to 0. No, then return 1. So this is my base case. Whenever the recursive call will come at this stage, it will always return 1. Okay. But here it is, the condition is not true. So I will come to the else portion. And in the else portion, we have if again. If 5 is even, this, if it is even, then we will use that formula. And when it is not even, then what is the other aspect? Odd. So I will come to this else portion, and we will use this second recursive formula here. So now 5 is what? 5 is odd. So this even will not work, and I will come here in this else portion. So this else portion will work, and it would be m power, b is what? 2, and 5 is what? 5 divided by 2, 2.5, and the floor function will give you what? 2. 5 divided by 2, what is the result? 2.5, and the floor function will give you 2. So 2, 2, and 3. So the else portion will work, and for m power 2, 5, 3, you will have m power 2, 2, 3 square here. Okay. So here this would be the situation now. And write other things. Mod m3. So mod m3. And b would be what? 2. 2 mod 3. Mod 3. So write that whole thing. 2 mod 3. Mod 3. Okay. So I have given these colors so that you can understand it. Well, otherwise it would take much time to understand. So now this is the call. This is the call to this m power method with these values, whatever it is. M power 2 to whatever it is. Now it is again called to this m power. And what is m power 2 to 3? This is the call. This is not the call actually. This is the calculation. This is the calculation. This is now the call 2 to 3. So now this is the call 2 to 3. Okay. So this is B, this is N, and this is M. So N is now 2, it is not 0. N is even? Yes, it is even. So now this portion will work. Then return M power. B is what? 2. N is 2. 2 by 2. You will get, what is the answer? Here I am not finding remainder. Answer. 2 by 2, I will get 1. So 2, 1, 3. So I am calling this M power again with 2, 1, 3 and mod 3. So let's see. I am in the else if where it is. So when I call this M power 2 to 3, here M power 2, 1, 3, 2, 1, 3, it's square and mod 3. How many students are with me on this calculation? Just raise your hand. Honestly. Don't raise your hands if you are looking at something else. Because some students behind, they are doing their own work. Don't say after that I have not explained that thing well. The recording is available. You can watch that recording again. But don't ever say or don't ever give this feedback that the teacher has not explained that thing well. It is not your right to say that thing if I am not explaining that thing. If I am doing something honestly, you must have to do your thing honestly. If I am, for example, if I do not like some person or if some person do not like me, that is something different, separate. Keep it separate. Anyhow, I am going very much slow so that you can understand these things. But if I will, so you can expect questions like that. And if you have those questions, don't say that this is complicated, this is tough, or this is hard. Anyhow, so 2, 1, 3, we are here. And the color is, what is that color? Okay, you can call it blue. So 2, 1, 3 is here. So I am calling this M power again with value 2, 1, 3. Okay, we are calling again. Now 2, 1, 3. So N is now 1. N is equal to 0? No, this condition is false. N is even? No, I will come to this else portion. And M power 2, 1 divided by 2. 1 divided by 2. 2, 0, 0. What is the remainder? It would be 0. How you can divide that? I told you already. 2, 0, 0 and 1 is the remainder. So you have the answer 0. So now B is 2. 1 divided by 0, you will get 0. And M is 3. So 2, 0, 3. This would be the call with all other values. So that's why M power 203, you are seeing it here. You are calling it again with 203. So N is 0. When N is 0, okay, return 1. Return that 1. So this 1 will be returned. And now you will have the actual calculation of your result. So this call will go where? This call will go here. It will come here. 203. So for M power 203 square, you have the 1. So 1 square, you will have you will have what value here? 1. What is the square of the 1? 1. And then 1 mod 3, and you can see things here. This is what you have here due to this portion. Due to this portion, you have 1. I can change the color here. Anyhow, you can see the cursor also. So 1 square is now here, and then mod 3, 2 mod 3, mod 3. It is the same thing. I am writing it again. Now evaluate it. 1 mod 3. What is this saying? It is saying that divide this 1 with 3. Now, but mod will focus on what? Remainder. Okay. Mod will give the modulus, the remainder. So what is the remainder now? 1. 3, 0, 0, and 1 is the remainder here. Okay. Now 1 is the remainder here, and what is here? 2 mod 3. Or you can say, okay, 1 multiplied by 2, 2 mod 3 is what? It is again, what is the remainder? 2, because that is 3. Allah Akbar, these are the simple. Look at the faces. Look at the faces of Aya Biru. Look at the faces of Nuh and others. 2 raised power 3. 0, 0. What is the remainder? When you have the word mod, it is focusing on the remainder. When you have this symbol division, it is focusing on quotient. Anyhow, so this 2 mod 3, what you will have? 2. Then you will have, when you will have 2, and then 2 mod 3 finally, what you will have? 2 again. So that's why 2 is mentioned here. So now 213 m power 213, this portion when you were calling, when you called it, what you have? 2 m power 213. And where you call this 213? This one. Here we are calling. Here we are calling 213. And what is the value for 213? 2. Put this value here, and for this blue you have this color. 2 raised power 2. Put this value 2 here. Okay, we have inserted that value. So 2 raised power 2 mod 3. 2 raised power 2 is 4. Now it's bigger. Now the remainder is 1. Because 4 you have to divide it with 3. 3 ones are 3. And out of 4, when you will subtract 3, you will get 1. So this is the value you have for this 2 to 3. Where you have called this 2 to 3? Here. Here you have called it in the yellow color. What is the value for this one? 1. Put this value here in this yellow color. And you have 1 square. And this is the square, okay? 1 square, and then mod 3 dot 2, write whatever you have here. Write all those things. And now calculate it. 1 mod 3, what you will have? 1. 1 multiplied by 2, okay, you can do it first or later, it is up to you. 2 mod 3, you will have 2. 2 and 1, 2. You will have finally 2 here. And then 2 mod 3, you will have again 2. So 2 is the answer now. 2 is the answer now. And it is also the understanding of this algorithm, how it is computing. So if you will give me 2 raised power 5 mod 3, 2 raised power 5 mod 3, 2 is the answer. Now, construct a recursive version of binary search algorithm. How many people know the binary search algorithm? Binary search. 1, 2, 3. What is binary search? How many people know that what is binary search? In which course you have studied this binary search? Previous semester. Okay, then I will not put too much focus on this question. Maybe you can understand this by yourself. Let's see anyhow. I can only explain the algorithm. I will not execute some example over it. For binary search, there is a condition. What is that condition? Before starting, it should be sorted. The list or the array, whatever it is, it should be sorted in ascending or descending order, whatever. If it is descending order, then you can, anyhow, you can change something in your binary search. So this is the condition, that your array or list should be in sorted order, only then it will work. So binary search, this I is the starting index, maybe J is the ending index, and X is the number that you have to find. And I, J, X are integers. And what is the value of I? I greater than or equal to 1. So I can start with 1 and it could be greater. And J would be greater than or equal to I. It is always, it can equal with the I or it can be greater with the I. But what is its limit? It should be less than or equal to N. N is some number, not number that you have to search, but this N is some limit. The last point of that array, last index of the array. If it is 10, then your array maybe will have 10 elements. And then what? In the starting, so binary search, it will take the starting index, J is ending index, and X is the element that you have to search in the array. And then what? You are adding this starting index and the ending index of the array. For example, the starting index of the array is 0 and the ending index of the array is, for example, 5. So 0 plus 5. But this is the algorithm, so you can take from 1 to 5, okay? Otherwise, 0 plus 5, it will work. But then you maybe, I don't know. Let's see what will happen. So 1 plus 5. If the starting index is 1 and the last index is 5, so if I is 1, J is 5, so I plus 1, 6. 6 divided by 2, you have 3. Now your middle, M is for middle point in the array. So if your elements has, if your array has 5 elements, then after dividing it, you have M3. M3 is the third element of your array. It is the middle point of your array. Now what? You will compare your element X, which you want to search, with this middle element of the array A. This is condition. You are just comparing that my searching element, which I want to search, if I want to search 25, so that 25 is equal to that middle element of the array. If the condition is okay, then return the location of that. Then this M is the index. Then return that position of the array, which is 3. So it means that our element has been found in the array at position M. Now what? If it is not the case, if our element X is not equal to that middle element of the array, then else if that, now we are checking that element X is less than that middle element of that array. M is that thing. M is the position of the element of an array. Okay, so this is the sequence you can consider. Previously you saw the sequence. So if this element X, which you want to search, is less than that middle element, then it is sorted, then it is always before that. Before that, it is your searching element would be before that middle element. If it is greater, then your searching element would be on the right hand side, if it is greater. So that is that thing written here. This only condition is sufficient, but there is one more condition is written here. What is that one? If I, which is the index of the array, which is going on, is less than that middle element. is if I just a minute. So if that is the rate, now this is the M. This is for example I. This is J. Okay, and here I am searching this X here. If it is equal, then return that M. If it is less than this M, then your element would be here on that side. If this X is greater than M, then this your element would be here on that side. This is what that condition is saying. So if X is less than M and I, the value of I is less than M is 3 and I is 1. 1 is less than 3. Okay. So then it means that my number is on the left hand side. Then return binary search. I am calling that binary search again with new indexes in which I is same, but I have to change that index. Maybe M minus 1 because this is we have checked this position. We don't have number here. So this M minus 1 is my now J. And then binary search I is similar and for J we are putting M minus 1. This is the value for that J. This M minus 1 will be copied here into this J. And then X is the element that we want to search. So we are calling this method, we are calling this our algorithm again. If it is not the case, then our X element, if it is there, then we have to change the value of I. J, you don't have to change this J. You only have to change this I. So if the number X, the element X is greater than middle element of this A, and the J is also greater than M, the J is also greater than M, yes, it is greater. Then binary search, change this M with M plus 1 because this is the starting point and now this is the ending point. So M plus 1 and the J and that element. And then you are calling that with this method again with those values. Okay. And else, if there is any other case, return 0. We have not found. This is, for example, I will do that one. And then after that, divide that, I will search here, I will search here. And if I will not find my element here, then finally your algorithm will come here at this position, else return 0. 0 means no, your element is not found in the, the index for searching that element is not existing in the array. So I am not explaining or running any example over it because you know this algorithm from your previous courses. But it is also mentioned here if you want to see in green color. So now what is the difference between recursion and iteration or iteration, whatever you want to say? So recursion, you know that recursion is something in which a algorithm call itself. That is called recursion. And iteration is what? In which we can rephrase this definition again. Recursion and iteration we use when we want to do the things repeatedly. This is one sentence which we can say. When we have things which we can solve by repeating that thing again and again. So here we can use the recursion and also we can use the iteration. But recursion is something in which an algorithm or method will call itself again and again to do that repetition. And the iteration is something in which you will write some loop for repetition. You will write some loop to do that thing repeatedly. You will do this thing by using some loop, not by calling some function. So that is something mentioned here. And this is just an example, the difference. These are the examples to illustrate the concept of recursion and iteration. Here it is a Fibonacci number. In object-oriented programming, you saw this Fibonacci series for this number. I am not going to explain it. And here we are calling that method again. Here we are calling that method again. So we are calling this method again, algorithm again. So this is recursion. And here, this is the same algorithm for calculating the Fibonacci series for some number, but without recursion. We are not calling this Fibonacci, this method again here in this algorithm. Here we are saying that if n is equal to 0, if the number you are given, if you want to find the Fibonacci series of some number, if that number is 0, return 0, 0 result. If you are giving some number, maybe 3 or 4, then 0 and 1 would be the first and the second number of that series. It is always 0 and 1 starting. And then what? By adding them, you will add them, and you will get 1 as a third number in that series. And what would be the fourth number? 1 plus 1. That would become 2. And then 2 plus 1, that would become 3, like that. So here we are using a loop which is going from 1 to n minus time. We are adding them, putting the result in that z. And then we are changing, this is the second number, this x is the first number. Now we are putting the value of second number in the x variable, which is the first. And then we putting that sum, which is z in the second number, which is this y. And then we are going on. Maybe we can use some output system.out.println here. And then your program will be completed, okay? So that is iteration or iteration. And that is the recursion. And these are the examples that you have to read and understand from the book. These are not exercises. These are the examples. And in midterm 2, I will focus on examples. In CO4, I have not mentioned the examples, but there the exercises are mentioned. So you should have to focus on the exercises there. But in this CO5, I have changed my policy. So I have mentioned only examples. So whatever written in the slides, you have to focus on those things. But for midterm 2, I will not give you any exercise. Just hold it. I should have